Okay, in this video we're going to take the information that you know about energy of photons and electrons and we're going to add some calculations to it. So to begin with, we need to do a little review about waves. When light or any other type of electromagnetic radiation travels, it travels like a wave. And the color of that light corresponds to a specific wavelength. And wavelength is from the crest of one wave to the crest of the other wave. And that is the symbol for wavelength. It's a Greek letter. And then we're also going to talk about frequency. And frequency is how many waves pass per second. So if you have a really short wavelength, you're going to have high frequency. If you have a really long wavelength, then you have low frequency. Wavelength is the actual length of a wave, so it's measured in length, which we'll use meters, and the symbol right here is called lambda. It's a Greek letter, and that's what we'll use to denote wavelength. Frequency is how many waves pass per second, so we're going to be measuring in 1/seconds, or seconds to the -1. And the symbol for frequency is the Greek letter nu. It's kind of a V shape. And then frequency and wavelength are related through the formula C equals wavelength times frequency, where C is the speed of light. All light travels at the same speed, 3.0 times 10 to the 8th meters per second. So no matter if it's visible light or UV light or any kind of radiation, it will always travel at the speed of light. Okay, so here's where we're going to do our practice calculation. So we want to calculate the frequency of light that has a wavelength of 5.00 times 10 to the -4th meters. So we're going to use our formula, speed of light equals wavelength times frequency. Now, we're solving for frequency, so we want to rearrange our formula to solve for frequency. So to rearrange our formula, we're going to divide both sides by wavelength. So the speed of light divided by wavelength equals frequency. Okay, so we know the speed of light. It's a constant. So 3.0 times 10 to the 8th meters per second divided by our wavelength that's given, 5.00 times 10 to the -4th meters is going to equal our frequency. So when we do that division, we get a frequency of 6.0 times 10 to the 11th, and our units, if you look in the meters cancel, our units will be 1/seconds. So that is the frequency of light that has that specific wavelength. All right, next example. This time we want to calculate the wavelength of radiation with a frequency of 1.50 times 10 to the 13th inverse seconds. So again, our formula, speed of light equals wavelength times frequency. This time we're solving for wavelength, so we want to divide both sides by frequency. So speed of light divided by frequency equals wavelength. Okay, so let's plug in our numbers. Speed of light divided by the frequency that's given, 1.50 times 10 to the 13th, and seconds to the -1st is the same thing as 1/seconds. So this time our seconds are going to cancel and our units will be in meters, and our answer is 2.0 times 10 to the -5th meters. So that would be the wavelength of that particular radiation. Now, once we know the wavelength and the frequency, we can figure out energy. So anytime heat or electricity, which are both forms of energy, are given to an electron to make that electron excited, we can actually calculate how much energy is needed to excite the electron. The amount of energy needed to make an electron move up one or more energy levels is called a quantum of energy. So you've heard that word quantum before. This is what it means. A quantum is a specific amount of energy needed to make an electron jump up an energy level. So the energy levels are different distances apart, so there's more than one value for a quantum of energy. And then when the electron moves back down to the ground state, it's going to give off a photon. And the photon will have the same energy as a quantum, it's just in a different form. The quantum of energy will be heat or electricity. A photon will be given off as light. They're all different types of energy, and we're going to learn how to calculate the amount of energy. Okay, so here's our atom, and here's an electron. Okay, it's in the second shell. So when energy is put into that electron, so when we put energy in, this is a quantum of energy. And then that electron is going to jump up to an energy level. It can either go up to 3 or up to 4. It can't go anywhere in between. It has to go to a specific level. So once it's here and it wants to go back down to the ground state, then the energy that comes out, that's our photon. So we put a quantum of energy in, we get a photon of energy out, and those amounts of energy are the same amount. Okay, so here's how we calculate energy. Our formula is E for energy equals H times frequency. Energy is measured in joules, which will be a capital J. H is a constant. It's called Planck's constant. Planck was a scientist that helped kind of formulate this whole idea of energy and photons, and so he named the constant after himself. Planck's constant is 6.6262 times 10 to the negative 34th joules times seconds, S for seconds. And then again, we use our frequency that has inverse seconds. So you can see when we multiply Planck's constant times frequency, the seconds will cancel, and we're left with joules. Okay, so here's how our example works. Calculate the energy of a photon of light with a frequency of 5.00 times 10 to the 15th inverse seconds. So our formula is energy equals Planck's constant times frequency. Okay, so this time we're calculating energy. We don't need to rearrange. So we're going to multiply Planck's constant times the frequency that's given. This time our seconds are going to cancel, so you can see our units will be joules. So our energy equals 3.31 times 10 to the negative 18th joules. So that's the energy associated with that particular photon that's traveling with that frequency. Okay, one more example. This one's going to be a multi-step example. What is the energy of ultraviolet light with a wavelength of 260 nanometers? NM stands for nanometers. And you see that unit a lot because it's a tiny little unit, and so we don't want to use nanometers in our formula because we need meters in order to use our speed of light formula. So the first thing we're going to have to do is take our nanometers and convert them into meters. Now, 1 meter is equal to a billion nanometers, and a billion is 10 to the 9th. So that means we have 2.6 times 10 to the negative 7th meters for our wavelength. Okay, now we want to find energy, and we know to find energy we need frequency, but we don't have frequency, we have wavelength. So how do we get frequency? We use our speed of light formula. Okay, so we want to find frequency, so we want to solve for frequency. So speed of light over wavelength equals frequency. We know the speed of light, it's a constant. We'll put it down here. Divided by the wavelength that we just found in meters, 2.6 times 10 to the negative 7 meters. Our meters cancel, and our frequency is 1.15 times 10 to the 15th inverse seconds. Okay, now we can solve for energy. We know that energy equals Planck's constant times frequency. We want energy, we know frequency, and we have the constant. So we're going to multiply 6.6262 times 10 to the negative 34th times our frequency that we just solved for, which is 1.15 times 10 to the 15th. And our energy comes out to be 7.65 times 10 to the negative 19th joules. So that's our answer. That's the energy of ultraviolet light with a wavelength of 260 nanometers.